All right. Why don't we begin today's colloquium? So the speaker is Stan Owocki, and he started his career here at CU, where he received his PhD in 1982, with work done at HAO with Tom Halser on the ionization state of the solar wind. Then he moved on to do postdocs at Harvard Smithsonian Center for Astrophysics and the University of California, San Diego. And then in 1987, he joined the Bartol Research Institute in the Department of Physics and Astronomy at the University of Delaware, where he is currently a professor of astrophysics. His research interests are largely centered on stellar winds and mass loss from massive stars, including also stellar wind-fed magnetospheres in the 10% population that harbor strong, large-scale magnetic fields. He retains an avid interest in the connection between physical processes in the sun and stars, including those of significantly higher mass. And today he will talk about radiation hydrodynamics in complex media, the sun versus massive star winds. So please go ahead, Stan.
Thanks. Well, first of all, it's really great to be back. It's like a bad penny; you keep coming back, right? I mean, it's 35 years. I have lots of fond memories of my time here at Boulder as a graduate student at HAO. Coincidentally, I was checking in at the desk this morning, and I ran into Tom Halser, who was my PhD thesis advisor. I got a chance to talk to him. As you may know, he's got some health problems. But hopefully we'll get a chance to maybe go out to lunch or something later before I go back next week, next Monday. But in general, I do feel like it's an opportunity to sort of reconnect back to a lot of the physics that I had learned when I was a graduate student here, when I was working primarily in solar physics. What's interesting is that as you go into other fields, you realize that some of the physics that you really care about is always a test bed. The sun is always a test bed for that physics. And so I'm particularly interested in talking to people about codes and methods that would be applicable both in the stellar wind context, or stellar context, as well as in the solar context. So basically, this is just to get a general background. Just a picture of solar granulation and a simulation of this. This is, I think, done by the Swedish group. But the key idea is that most of the structure you see for granulation is many megameters or thousands of kilometers in diameter. The inner granulation lanes sometimes have these bright points, which can go down to very small scales. But one of the key things that I learned when I was a graduate student here, as Larry Auer put it so succinctly, photons know which way is up. And the reason they know which way is up is because the gradient, which is set by the hydrostatic pressure scale height, in the vertical direction is always the scale height is quite small, so the gradient is very steep. The opacity scale height is less than 100 kilometers a second. That should be 0.07. That should be 70 kilometers, not 7.07, 1/10 of an arc second. And these things are on the scales of thousands of kilometers. But of course, in the regions of the bright points of these that could be quite important. So the very first, I should also mention that the very first paper I ever wrote was with Gordon Newkirk, former director of HAO, on bouncing radar signals off of the solar corona and using them. There was a guy named Jesse James who did work in the 1960s. And basically, I did a project on trying to figure out what would we expect by bouncing radar signals off the solar corona. And it turns out it was actually seen, but there were a lot of limitations to the instrumentation at the time. And I think every few years that becomes an item of interest again, is whether you could learn something useful by bouncing radar off of the sun. So, but the next project I worked on was based on this code that Dimitri Mihalis and Larry Auer and Barbara Mihalis wrote in 1978 on developing one of the first codes for doing radiative transport, two-dimensional radiative transport in a planar geometry applied to the sun. And Jeff, at the time, Jeff Linsky, was looking for summer students, and I had just taken Dimitri's course on stellar atmosphere. And Jeff basically was willing to hire me for working with him in the summer. And what happened was he was interested in trying to understand what the effect of two-dimensional radiative transport might be on the emission lines from calcium H and K. In particular, when you model those lines, you see very strong double reversal, a deep double reversal. When you observe it, that double reversal is pretty well filled in. And we wondered whether maybe two-dimensional radiative transport might play a role in that filling in. Well, that project evolved a little bit, and then that fall, Larry Auer and I started a project where we just basically applied this code to just understanding the transport in the wings of the calcium H and K lines. And Larry, when I started this project, it was quite an interesting experience working with him. But then he had a car accident, and he drove off of the mountain in Sac Peak, and he was in the hospital for about a year. And during that time, I wrote this paper. Dimitri was the local internal referee on it. Anyway, I learned a lot about radiative transport flow from Dimitri's class in this paper. And as Larry had said, the key thing is that the lateral transport, when you actually have to worry about photons going laterally as opposed to going vertically, really is limited in scale to something on the order of the scale height. But we showed in this paper that it actually depends on the thermalization destruction probability, sometimes also written as an epsilon. I have another interesting story during one of my exams, which Jeff was sitting in on. Well, actually, I think it was at the end of when I was going to be interviewed for this job. He turned to me and he said, "What's epsilon?" And I said, "I don't know, but I'll bet it's damn small." So anyway, in the wings of the lines, this epsilon is this psi parameter is about 1/10 or so. So you can get a few scale heights horizontal transport before material will escape vertically. And that means that that's the scale you have to worry about lateral transport. Only a few hundred kilometers, which is a sub-arc second. And nowadays we have to worry about that. In those days we were just anticipating high resolution instruments being built. But then I moved on to working with Tom and Art Hundhausen on trying to use the solar ionization state as a diagnostic of the solar corona. Basically what happens is the ionization state of the solar corona freezes in because the density gets so low. And so you can actually learn a lot about conditions in the outflow in the inner regions of the solar corona, which are so important for understanding the dynamics of the solar wind. Of course, this picture was taken with one of the HAO eclipse expeditions. I think this was done in the 1970s, where you can see the beautiful structure, the striated structure of the solar corona, due to the fact that the outward expansion of the high temperature gas into the solar wind is being confined by magnetic loops here. And eventually, though, the solar wind wins out and it pulls the loops into these radially streamers called helmet streamers because they look like a German World War I army helmet. So what I'm going to talk about today is mostly focused on my work on stellar winds. To give you the background, you have winds like the sun's in other main sequence late type stars. Due to the fact that the sun's corona is so hot, it wants to expand in the interstellar medium due to the high pressure. But the winds that I'm going to talk about today are driven by radiation, by the light scattering off of ions. The temperature is much lower. The mass loss rates are up to 1 billion times higher, even 10 billion times higher. And sometimes these winds can have enormous eruptions. For instance, in Korea, they actually lose a solar mass per year, with the sun's losing 10 to the minus 14 solar masses per year. You can also have cool supergiant winds. At the end stages of the sun will probably lose about 10%, maybe 10 or 20% of its mass before it becomes a white dwarf in one of these winds. But the winds that we're going to talk about mostly today are due to radiation driving. And the reason I picked this topic is, well, first of all, here's the pictures of the solar wind. And quite in contrast to the simple analytic model that Parker developed, the solar corona is very, very dynamic because of mass ejections and so forth. But the dominant amount of mass is in the quiescent. The mass ejections only end up being a few tenths of a % of the total amount of mass loss. Now, it turns out that, and there's Venus, it turns out that there are a subpopulation of massive stars that have very strong magnetic fields. They're not generated by a dynamo. We don't know exactly where they come from. They're very stable, and we can basically model the stellar winds in those cases where the material, because it's very dense, it actually cools back down and makes these high density loops as the material collides at the top of the loops from each foot point. And what happens then is that material can either fall back down, or if it's rotating, it can be supported centrifugally. And the key radius is where the magnetic energy density dominates over the flow energy kinetic density of the wind. And so I've defined this parameter eta, which is like beta, except that it's upside down, and it involves not the gas pressure, but the wind dynamic pressure, which involves the mass loss rate and the terminal speed. And then because the field is falling off for a dipole 1 over r to the 3, which means the energy density falling 1 over r to the 6, eventually the wind gets pulled open, just as it does in the solar corona, into a radial configuration. Anyway, so this is just an example of some of the work that we do nowadays in trying to model these dynamic corona. Let's see if I can get the movie to play. Is it playing? It doesn't seem to, oh, there it is. Yeah, so you can see material basically gets trapped, cools, and falls back down. And you see X-rays being generated by that process. Anyway, you can also see the H-alpha emission from this. But I'm not going to talk about this today. However, this is a real area where there's a potential, a lot of mutual discussion we could have about the role of magnetic fields in outflowing plasmas like the solar corona. So if anybody's interested in this, please, contact me afterwards. Now, so I want to start off with just a basic review of solar wind theory. So basically, the equation of motion says that you have inertia, which is acceleration. This is a steady state equation of motion. Gravity, pulling you in, gas pressure, and then some external force. And then if you basically use the fact that for steady state, the total mass loss rate is 4 pi r squared rho v. If you then use that as a constant, you can solve this, and you're all familiar with this. You have V minus, the pressure breaks up into a part that depends on velocity and a part that depends on geometry through the continuity equation. And so what you find is that the left-hand side and the right-hand side go to 0. Suppose in the solar corona, you can ignore this. It's not completely ignorable. There may be alphane waves that are giving you extra momentum addition. But mostly it's just a matter of the right-hand side and the left-hand side going to 0 at the same point, and that occurs at the sonic point. A here is the isothermal sound speed. And so what happens is that when you solve that, you get a ratio of these two things. You use what's called L'Hopital's rule to find out what the gradient is, and you find out that it solves the quadratic equation, and you get this what's called X-type critical point, where the solution of the wind goes from subsonic to supersonic. This is the solar wind. Now, interesting, one of the things I do with my students is that when I'm teaching them hydro, one of the first problems I have them do is to take a hydro code and just start out with a hydrostatic corona. And when you do, you find you start with the hydrostatic corona because the right boundary has very low pressure. The gas at the right boundary wants to flow outward if you put a vacuum at the right boundary. And at that point, then the wind starts to have a rarefaction wave that moves back, and it makes the solar wind. So this very idealized steady state model is a very stable solution in the ideal case where you just have an outflowing spherically symmetric outflow. And basically, it's an attractor. This weird solution that goes to the sonic point is the only solution that satisfies the boundary condition at infinity, that there's no pressure. Now, in hot stars, the gas pressure is actually very low because, unlike the solar corona, which has millions of Kelvin in temperature, in the sun, in these hot stars, the radiation losses are very dominant, and the photosynthesization heating from the star, which is of the order of tens of thousands of Kelvin, is dominant. So the sound speed tends to be on the order of 20 kilometers a second, whereas the gravitational escape speed from a star is hundreds, or 600 or 700 for the 624 for the sun. So the energy in the gas is nowhere able to make a wind by gas pressure. So the lesson is that all these terms that are so important in the solar corona become negligible in the case of hot stars. And that means that you can throw out these gas pressure terms pretty readily, and without sacrificing too much realistic physics. And all you really have to do is solve the momentum equation, which is the inertia acceleration of the gas, advective acceleration, is gravity plus radiation force. The only way you get a wind is to have radiation force be bigger than gravity. So the next question is, when do radiation forces become bigger than gravity? So basically, photons are trying to come out of the star. Gravity is pulling inward. And we're putting a radiation force that depends on the integral of the opacity times the flux divided by the speed of light. Because you take flux divided by the speed of light, that gives the momentum per unit time. Then you multiply by its opacity per time per area. Opacity is centimeters squared per gram. This gives you an acceleration. And so that's the thing you have to know And the trick, of course, is that you don't often know what the flux is as a function of frequency and opacity. You have to solve radiative transfer in order to do that. But the simplest case is imagine you just have a free electron scattering as a free continuum opacity. Well, then this integral becomes trivial. This becomes the you pull the electron scattering out. It becomes the bolometric flux, which is just luminosity over 4 pi r squared. And gravity also falls off like over r squared. And so the ratio between these two things, the electron scattering force and gravity, is a constant. And this is called the Eddington parameter. It's where Arthur Eddington first realized that when this parameter got to be of order unity, the star could not be completely bound. So we call that the Eddington limit, when gamma E approaches 1. Now, in general, however, the formula for this parameter of radiation force over gravity can be written in this nice scaling form that it's only a factor about a 10 to the minus 5 for the sun. In other words, you can ignore radiation forces for the sun because the sun, it's only about 1 over a couple hundred thousand, well, 2 times 10 to the minus 5. But the point is that this opacity is also not limited to electron scattering. You can have other sources of opacity. And so this is the thing you have to worry about. All right, so next, let's go on to find out, well, what is the most dominant source of opacity? Well, surprisingly, it's in lines. Lines have this enormous capacity to scatter photons, line-bound transitions. The analogy that I like to use is, imagine me blowing, right now, just watch me blow air. You can hear some noise, some white noise from that. But if I'm good enough, I can't do it right now because I've had a beer at lunch. But if I could, if I could make a whistle, you would hear, for the same amount of pressure, a very loud sound, which was tuned to a specific frequency. That's because the cavity inside my mouth is like a resonance, and it enhances the effect of the energy coming out of my lungs into the air to convert that into sound. Analogous effects happens when atoms are bound electrons are bound onto atoms. Their cross-section goes up by an enormous factor. The factor is of order 10, believe it or not, 10 to the 7. It's the ratio of the lifetime of the atomic state to the frequency of the photon, to the period of the time, the period of the photon. And that's an enormous, the other way around, I guess. And that's an enormous number. And even when you take account of the fact that only a small fraction of electrons in an atmosphere are bound onto atoms, when you talk about a massive star where hydrogen is completely ionized, you get an enormous radiation force. If you could expose lines to all of the radiation force, all of the flux, an unattenuated continuum flux, the radiation force would be 1,000 times free electrons. That's a combination of this resonance and the fact that there's only 10 to the minus 4 of the atoms that are in bound electrons. So now, the next thing is that in reality, that you can't expose all the photons because lines very quickly saturate. They use up all the few photons that are right in the middle of the line. So the line becomes saturated. You don't have any photons at line center. So you have this weird competition, right, between having lots of opacity but not many photons. And so normally that limits how important lines are in a stellar envelope. The Rosslin mean opacity, which is sort of the harmonic mean, taking into account the fact that photons avoid the center of lines, is actually only a factor of a few order unity bigger than electron scattering. But what happens in a stellar wind is once you can get the gas going, the lines will now see photons be redshifted from where they started. So photons that are started out in the continuum now get resonantly Doppler shifted into a resonance with the line. And so the line sweeps through the spectrum and eats out up to V infinity in Doppler shift, or about 1% of the spectrum. Each line will work out because V infinity is about 1%. And so you have this really, quite interesting coupling between the acceleration of the gas and its Doppler shift, which gives rise to the ability for the lines to actually operate. And so you have this kind of effect where the photons leave the star. They think they have made it away from the star. Now they're going to propagate freely. But if they're on the blue side of the line, the red shifting of the line makes them Doppler shifted into resonance with the line. And they interact with the line over this narrow band at some resonance point. And what this means is that now radiation transport becomes very special because it has this character where the photons are basically free streaming until they go into resonance. And then the conditions in that resonance layer are very homogeneous. And so you can talk about the radiative transfer in that resonance layer in a very simple way using escape probability methods. And the net outcome is that the radiation force only depends on this collection of parameters. The radiation force is the optically thin force, which is just flux divided by r squared, luminosity divided by r squared times opacity, divided by this correction for optical depth, where the optical depth is called the Sobolev optical depth. It's the opacity times the density, which is 1 over length, times this length scale, which is called the Sobolev length. So this localizes the radiative transfer. It means that we can do radiation hydrodynamics in expanding atmospheres of stellar winds using a local treatment of the radiation transport, which has a really weird combination between free streaming and diffusion. Okay, but because we can talk about the resonant layer, we can do that very accurately, and we don't have to solve a global radiation transfer equation. And this is always the problem with radiation transport, is that it tends to be non-local. So that's really all well and good. So it turns out Castor, Abbott, and Klein used this basic approach to solve for stellar wind solutions, mass loss rates, and so forth in the 1970s and 80s. And that model has survived in its basic form with various adjustments over the last 40 years. It's really quite a remarkably successful theory. I came on the scene asking the question, what happens if you make a perturbation in that radiative-driven wind? In the early 80s, I went to work at CFA, worked with George Rybicki, and we asked the question, what happens if you perturb such a stellar wind? Well, the first answer is pretty straightforward. If you make a perturbation whose length scale is large compared to this Sobolev length, this resonance width of the resonance layer, then it just gives you a radiation force which is proportional to the velocity gradient. And then that means that velocity gradient, when you take a gradient of a velocity, it's 90 degrees out of phase if it's a sinusoidal wave. And that means that the velocity, the radiation force and the velocity are always 90 degrees out of phase. And all that does is change the propagation of a wave. It basically makes it propagate at a speed back towards the star, which is of order the ratio of the flow speed. And this led to Dave Abbott writing this beautiful paper using analogies between the solar wind critical point and the sonic point and the critical point of a line-driven wind, which was due to these Abbott waves. Well, he didn't actually know about the Abbott waves yet. But anyway, well, I guess he was in there, yeah. So anyway, well, he didn't know about the Abbott waves because he was Abbott, right? I mean, he got named after him afterwards. But, so this turns out that if the waves are long wavelength, they just propagate, they just give you a new radiative acoustic wave that propagates through the stellar wind. But now, what if you make a perturbation that's small compared to the Sobolev length? Well, now you can show that the radiation force, the perturbed radiation force, scales with the perturbed radiative velocity, not its gradient. And that means that you have a force that's faster. It makes the wave want to grow instead of propagate. So this leads to an instability. And this is called the line-deshadowing instability, because the nature of this instability is this. If you have, imagine that this Doppler broadened line profile, opacity profile, has been sweeping through the wind, and it's just about to eat the photons on the blue edge. And the integral between this and the influx that's still coming up from below, that integral gives you the radiation force. But now if you Doppler shift that profile a little bit to the faster speed, it now eats extra photons, this extra area, and that extra area is proportional to the velocity gradient. And when you do the arithmetic, it turns out that this is a very powerful instability. It leads to growth rates of the flow time through a Sobolev length, which is 100 times the wind expansion rate, which means that you expect e to the 100 growths of this instability. So line-driven winds are very unstable. And so I did the first nonlinear simulations of this using a pure absorption model. We just imagine the lines are just absorption lines. We get a radiation force which is still G thin divided by tau, where this alpha parameter is a mixture of optically thick and thin lines. It's typically 0.6 or 0.7. But now we have to do this optical depth non-locally. It's an integral optical depth. And that's a key difference between what happens in Sobolev radiative transfer, where everything is purely local. Now we have a non-local integral to do at each time step. And that's, of course, quite costly to do numerically. But sure enough, the growth, the wave, a little perturbation here grows to very large amplitude. This is inverse density. This is very dense material. It's been compressed by this shock. And that's the kind of structure. And that was done in 1988. That's actually, to this day, my most highly solid paper with John Castor and George Rybicki. Okay, so now we go back to some really unexpected surprises. The first unexpected surprise is when we tried to study the topology of the steady state solution. This was work done with Clint Poe, who was also a postdoc here around 1989 or 1990. He worked with Keith McGregor. And Clint and I, when I was visiting Boulder, I think in 88 or 89, spent the summer working on this issue. And here's the point. We remember that we have now this acceleration, this equation, the numerator and denominator. Well, now instead of just having the sound speed and this one here divided by the velocity gradient as the ratio of these two things, now we have this line force. Okay? And it turns out the line force itself depends on the velocity. So whereas in a standard solar wind model, this is just a simple X-type, this is a solution that has a positive slope and a negative slope solution at the critical point, now it becomes a quadratic equation where, depending on what the coefficients are of how the radiation force depends on velocity, you can get either a positive and negative solution slope, or you can get two positive slope solutions if A is less than 0. And indeed, what we found is that you could get some very peculiar behavior, that you could get something called a nodal critical point. This is actually stuff that Tom Holzer wrote a series of papers on, nature of critical points, in the late 70s. And instead of having this beautiful this simple X-type solution, which gives you this nice stable solar wind, you now have two types of solutions: a steeper solution, which turns out to be quite stable, and this one, which is terribly unstable because there's a whole family of solutions that mimic it going through the sonic point. And so it turns out that if you can have boundary conditions that favor the steeper slope solution, if you have boundary conditions that favor the steeper slope solution, you can actually relax to a nice steady state. But if you have boundary conditions that otherwise pick one of those lower slope solutions, which is actually more analogous to the CAK model, you get this kind of relaxation oscillation going on. And the wind is inherently variable. It's sort of a series of steady state solutions. This is even independent of the line-Deshadowing instability at small scale. So anyway, it turned out that this depends a lot on the ratio of the thermal speed to the sound speed. This is done in 1990 with Clint Poe and John Castor. All right, so that's where things stood until the early 90s. And then what happened was, we had been criticized a lot by Leon Lucy, who is another real expert in this field, for not including the fact that the photons are not absorbed, they're scattered by the resonance. The lines that drive stellar winds are scattering lines. So another way to look at it is that in this slightly different picture, here's the line frequency, here's the broadening, the thermal broadening about the line, and then the photon becomes Doppler shifted as it moves out through the wind. And when it gets Doppler shifted into resonance with the line, it starts out at a wavelength below the line wavelength, which is higher frequency, red shifted into the line. Now it has to fight its way through this. But eventually it does that. This is showing as if it were to fight its way as if it were coherent scattering. It turns out it actually redistributes to the core and then bounces around here. But the net result is that when it finally escapes this resonance zone, it moves away, it's more or less 4F symmetric. And that means that it's 4F symmetric, it doesn't impart any net force. And therefore you can ignore it to first approximation. In the Sobolev limit, it doesn't give you any radiation force. So people had always assumed that no big deal. But it turns out now we have to worry about this because now we have structure in the field. So if we go back to this original diagram that gives you the instability, now if we put in the diffuse radiative component of this diffuse force instead of the direct component, you find out that there's a term that it goes, the net difference between the forward and backward streaming diffuse flux has this character that the backward streaming has a bigger contribution than the forward streaming, and that gives rise to a drag effect. And this is first introduced by Leon Lucy in a beautiful paper from 1984. Now, so while we have to put in this diffuse radiation force, we can't just solve pure absorption. So now that becomes a more difficult radiative transfer problem. So now this you can lower the instability. Instead of getting 100 volts, you still get 50, but it actually stabilizes the base. The base will actually become stabilized. So in the early 90s, I tackled this problem, and I came up with a series of methods based on the concept of escape probability. Escape probabilities are often characterized in terms of a single escape probability from certain places. Anybody here on radiative transfer theory will be familiar with this. But now the idea is that these escape probabilities require you to do an integration, a frequency angle integration, a frequency integration over the line opacity, over the line profile. So this paper provided the basic mechanisms by which we could solve this problem. And in particular, we came up with a really remarkably simple model that seems to carry a lot of the physics in it. And I'm very, very proud of this model. It's called the smooth source function model. So the basic idea is that everybody familiar with radiative transfer knows that this is the formal solution of for the intensity from scattering or from any kind of source function S. Depends on the integral over optical depth of the source function. Now, when the source function for pure scattering is just the mean angle averaged frequency and angle average intensity. So the problem, of course, is always you need to know the intensity in order to get the source function. That's the problem with scattering. But what we have is that this is averaged over frequency and angle. So all of the detailed dependencies on velocity and direction that occur for the instability are now averaged out. So the expectation is that this function is a much less complicated, spatially complicated function than that. And so a good approximation is to say, let's just replace the dynamically varying source function with the some local approximation, which is not dependent on the integral, the prime. And now, of course, that means that you can take the source function out of the integral, and now anybody can do that integral. Even I can do that integral. It's just e to the minus t, right? So now you have this way to get the diffuse force, which depends on this, which is depending on the escape probabilities in the different direction. That is the angle. This is now the core radiation coming from the star depends on some sort of escape probability. That's the term that gives rise to the instability. This is an integral escape probability. It depends on the integral optical depth that we talked about earlier. But now we could actually do this as well. And the diffuse force is just taking forward and backward directions, integrals of this in different directions. And that force now in the Sobolev limit, there would be 4F symmetry, and this would be 0. But in the non-Sobolev limit, you end up getting a non-zero diffuse force. And that diffuse force plays a big role in the dynamics, the radiation hydrodynamics of this medium. So here is a one-dimensional simulation of this process, if I can get it to run. Did it run?
Yeah.
Sorry. Oh, it was running. This is not running on my screen. Okay. So you can see that what happens is that you just automatically get this very complicated structure. Lots of density flux. This is density. This is velocity. This is temperature. Every one of these shocks makes this little spike in temperature. And but notice that the base is very stable because the drag effect stabilizes the base. All right. Well, that's great. You get basically everything. And it doesn't take that much more computational resources because the same integral optical depth that you use to calculate the direct force can be used to estimate the diffuse force in the different directions. So this only added about 20% to the numerical hydrocode in terms of time. But this is all one-dimensional. And we'll come back to that in a second. But here's the basic result, that the model basically follows a standard Castor-Abbott and Klein steady state model with lots of fluctuations, but the line drag stabilizes the base. And backscattering also means that information is propagated from upstream back into the base, and that causes perturbations, which then self-excite the wind. So once you have instability, it always is there. It's just basically self-perpetuating. And because radiation can actually propagate upstream at the speed of light, and therefore it can backfeed perturbations at the base. Okay, so, however, if you just make a slight change, if you account for limb darkening of the radiation from the star, it turns out that the space now becomes very unstable. And so we scratched our head over this, and we realized that this is all the same kind of thing that happened with the pure absorption models. If you avoid limb darkening, this A coefficient will stay positive, and the wind just relaxes to a steady state with this instability away from the base. So this is the base, this is the time versus radius, and now you can see the model just settles down to a nice periodic, one-dimensional nice state. But if you now start to add reductions in that feeding of the radiation, make it more pointed as opposed to having limb darkening, that coefficient starts to become close to zero, and now you start to get intrinsic variability. And if you go to the point where you add limb darkening, then you get this very dynamic structure. So the bottom line is that the winds are actually unstable right to the base if you put in more realistic physics. All right, now we have to ask ourselves, what happens? This is all one-dimensional. Nobody's going to believe one-dimensional. We know that the winds are not one-dimensional. So the first approximation to attempt this, because it does take so much time to calculate the characteristics, is just to do what two-dimensional hydrodynamics, but do a one-dimensional radiation transfer along a characteristic ray going back towards the star. And when you do this, the instability appears just as before, but now you can see it breaks up by really Taylor instabilities. And this turns out if you study the scale of the lateral structure that forms, it can actually go down to the grid scale, which means that you're not actually fully resolving what would want to happen. Really, Taylor will become the smallest scale possible. But, so here's a summary sort of what happens in this two-dimensional 2DH, 1DR. Basically, shells basically turn into structure, and then you get this very, very complicated structure, where the structure has a scale. This diagram basically says, let's take 15 degrees of azimuth, and then it just sort of takes time and it patches them together, so you can see the full global evolution. So now, so if we could figure out what the right scale would be, we could explain, for instance, on Wolf-Rayet stars, they show this variability in their emission lines. And the variability tends to go from line center to line wings. And these are from observations, time-resolved, very high signal-to-noise observations of emission lines from Wolf-Rayet stars. And this is a model that just basically tunes the scale of the horizontal structure to be about 3 degrees, taking a one-dimensional model and basically randomizing it over 3 degrees in azimuth. And you basically get a very good agreement between what you see in the emission line spectra. So the next step will be to try to figure out how to really solve the scattering problem in multi-dimensions. And the problem is that you can't use a diffusion model. You can't use even a short characteristic model, because this model inherently, these stellar winds inherently have long streaming photons, which then all of a sudden become very diffusive. So it's the nightmare case for somebody who wants to do radiation transfer. You can't use either. You have to do long characteristics. So we came up with this first approximation, the first attempt to do this along rays, basically 3 rays, 2 lateral rays and 1 radial ray, and then applied that in a pseudo-planar model where we basically artificially put in the 1/r² variation in mass flux and radiation. But then, because we have a planar model, the rays intersect grid points which greatly facilitate the integrations. And what we find is, again, if the structure breaks down into lots of small scale structure. However, now the structure has a finite scale that's larger than the grid scale, the lateral scale structure. And so here is a calculation of the two major statistical quantities you want: the clumping factor, which is the average of the square of the density over the square of the average density. And that's about a factor of 4. It's roughly what you need in order to explain various observational diagnostics. But now this is the length scale is about 1/200th of a stellar radius, and there's about 1,000 zones horizontally. So this is several numerical grid zones. So it is well resolved. Okay, so what is this relevant to? Well, one of the things you see from these massive stars is you see very broadened X-rays, whereas Capella is a coronal source where the X-ray emission is very narrow. These X-ray emissions from these stars, they're coming not from the gas. Most of the gas is very cool, but when it shocks in these instabilities, it gets very hot, and you get X-rays from that. But because the wind is now expanding away, you basically get very broadened profiles. And so what you have to do is solve the radiative transfer equation along these different trajectories with constants of constant optical depth of the observer, and then synthesize a line profile from the emission from X-rays. So basically, that's what you see. That's what you model. You tend to see a blue shifted because the material coming towards you doesn't have as much column mass to absorb in front of you. The material that's emitted on the other side of the stellar wind over here has to travel all the way through the wind, through all that cool gas. And the bound-free absorption, continual absorption of the bulk of the wind, absorbs these red-shifted photons because the gas is mostly cool. X-rays are emitted from the hot, thin shell gas, but the cooling length is very short, and then it goes through all this cool gas to get to us, and that's where it's absorbed on the blue edge. And the amount of asymmetry is a direct diagnostic of the mass loss rate. This parameter controls the mass loss rate. You can see as you go to increasing mass loss rates, or increasing this optical depth parameter, you get more and more asymmetric profiles. So here is a case where you actually try to fit the data from a zeta Puppis, and you find out that you have to lower the mass loss rate to about a factor of 2 or 3 below what people had thought the mass loss rate of that star was in order to explain the X-rays. We think that these mass loss rates are overestimated because many of the other diagnostic depend on the density squared, which is enhanced in such a stellar wind because of the clumping. And so now the question now becomes, how important is clumping for this bound-free absorption, which is a single density diagnostic? Well, the point is that when you take clumpings, and if you can make the clumps optically thick, then the medium, the same amount of material, will be less absorbing. So there's this parameter called the porosity length, which depends on the scale of the clumps divided by the clumping factor -1. And that, as you increase that parameter, make it bigger and bigger, you make the medium more and more transparent with the same amount of mass. So one of the ways you could explain the fact that the mass rate that you infer seem to be so much lower is that maybe they're being artificially lowered by having optically thick clumps. So this effect is called porosity. And it's an effect, if you think about it, just having a clump, its cross-section is of the order of its area squared, but the amount of photons that get absorbed by it are 1 minus eta minus tau of the clump. The tau of the clump depends on the density of the clump times its scale, which can be written in this combination of parameters, where h is this porosity length. And then the effective opacity is reduced by the real opacity divided by the optical depth of the clump. So if clumps become optically thick, if they're optically thin, then there's 1 minus, this just becomes tau over tau. You just recover the microscopic opacity. But if the clumps become optically thick, you reduce the effective absorption of that medium. And so that's something called porosity, and it's something that people worry about for very complex medium. And so we did an exploration back in the mid-2000s about how this would affect. And it turns out you have to have porosity lengths that are very large before you could make them a profile that would normally be very asymmetric to make it more symmetric. You have to have this porosity length be on the order of the stellar radius. And that requires either very optically thick clumps, big clumps, or very dense, very large clumping factor. All right, so now the next step is to say, can we quantify the porosity that you actually get from the instability? So, this is, let's see. Can we quantify the porosity? So this is going to take you through a little bit of what is pretty straightforward. The first thing to do is just to take some segment through the wind, any direction of a length L, and then ask what the optical depth over that length is. And then define an average of just taking an ensemble average of that process, because now this is a stochastic variable. And then just define a quantity which is the ratio of this to its average. This is like a mass column scaled by the average. And then to get the actual extinction through a path length, you take the average over the ensemble of e to the minus m tau, because that's the optical depth average. But because this is taking an average over a very nonlinear process, the average of this is not just e to the minus tau average. It's not just e to the minus tau. It's e to the minus some other quantity. And it depends on the distribution how much material is in different mass lengths. So the key is to get this mass column right here. But we can get that out of the simulations. And what we find, if we take a little path length, we get a very broad distribution. If this were a smooth medium, this would be a delta function. But now you see, as you go to very larger and larger lengths, it averages over more and more structure, becomes more and more like a delta function. But for smaller lengths, it basically is broader. So now if we plug that data into here, we find that the extinction, instead of being, this is the extinction on a log scale versus linear tau, that's e to the minus tau. But now you see the extinction is less and less and less as you go to smaller and smaller length scales. So this means that transport is no longer simple exponential. It has some very different non-exponential. This is the effect of porosity. So now what we want to actually figure out is what is the associated porosity length. Well, what we do is we fit this distribution with an analytic function. We do the integral analytically. It ends up being something, anybody here knows about the kappa distribution? It's often used to describe the solar wind. This is basically a kappa distribution. And you can see that the solid lines, the analytic function, fits the numerical data very well. But now we have an analytic function, and it turns out that the link between length and this parameter t, this parameter t naught is just this given by this, where h is some porosity, like turbulent porosity length. And so you can write that as just 1 plus tau, and that's how we got this formula. Anyway, this is really great. I'm really proud of this, and anybody who wants to know about radiation transport and complex medium, I think this has a lot of potential to be applied, because this gives you a simple way to treat transport in complex medium with a simple rescaling of the opacity. And you think about that. Now that means a complex medium density. All right, because this is a very, so for instance, the interstellar medium is very complex density. You could potentially ask yourself, what is the porosity? So when you actually work out, if you take the average of that function where it's normalized now, if you did this for exponential, this would just give you 1. That just says you typically go 1 mean free path when you do radiative transfer. But now, this path length depends on the porosity, on the optical depth of a porosity length. And so what we find is that the numerical calculation of this quantity, which is the black curve, matches very well the square root of 1 plus tau h. As you increase the optical depth of a porosity length, you basically follow this. So this is the big result. I could put flashing signs. This is an amazing result. This tells you that in a complex medium, if you can figure out what this porosity length is, you're well on your way to basically modeling the radiation transport in that medium, if it's a very clumpy medium. All right. So what does this apply in the context of these winds? Well, the clumping factor is about 4, as I said before. But the scale length is very small. So when you plug those two things together, the scale length, which represents the size of the clumps, the turbulent porosity length is very small. It's about 2% of the stellar radius. And so this medium is completely unporous. You can just basically forget about porosity for calculating. In other words, if you plug this back in, this tau h is going to be very, very small for any kind of optical depths of the wind that are reasonable. And that basically means that you can forget about porosity generated by the instability. So the basic result here is that LDI porosity is very small and it should have no effect on line transfer. To get X-ray line symmetry, we need to lower the m dot or come up with some larger scale structure. All right, now I want to now take this to the next step, because this kind of problem of radiation transfer in porous and very complicated density medium will occur. This is a beautiful paper that I refereed, actually, by Yanfei Zhang and collaborators from Santa Barbara. I was actually at one of those KITB workshops last year. Anyway, there's instabilities due to the iron bump that basically now are done with a full three-dimensional radiation hydro code that solves the actual, it's an amazing it's amazing code. And it basically solves what structure you get at the iron bump due to the fact that there's this opacity peak. And you get this very, very complicated structure. And the point is that you can see that the radiative flux is always higher where the density is always lower where the density is higher, and higher where the density is lower. So this is porosity. This is an example of porosity. And I've been trying to get Yanfei to sort of test to see how well this model, this analytic model, might work. All right, now the next thing I want to do to close is talk about stars that actually reach the Eddington limit. So we've been talking about up until now is winds that are driven where the electron scattering radiation force is still a little bit below gravity. But now when you add the line force, you can get this steady state wind, which then is perturbed by these instabilities. But sometimes we find stars that actually go above the Eddington limit, the classical Eddington limit. Certain times there can be, you can have situations. Stars can merge, and then when they merge, all that extra energy gets dumped in the envelope. Or you can have wave deposition. And in particular, when stars get close to the Eddington limit, they can basically have this variability, this highly variable, called luminous blue variables. And one of the questions we have is then how do we model what happens? So you can see the kind of mass loss ejection events that you get from stars that are close to the Eddington limit. The most famous is Eta Carina. Eta Carina had an eruption. It lost more than 20 times the mass of the sun over a period of about 10 years in the 1840s. Can we explain this with radiation hydrodynamics? So I've been working on that problem for about maybe 10 or 15 years. The first thing to realize is that Eta Carina's eruption, the mass loss rate cannot be explained by line driving. It's basically 1,000 times more than you can explain with line driving because lines will inherently saturate and they cannot really drive so much mass loss. The second point is that the observed luminosity of Eta Carina during the 1840s was about factor of 5 above the Eddington limit. So the star was above the Eddington limit at the time. And the final point is the amount of mass that was lost times the energy, times the kinetic energy was comparable to the luminosity. And this suggests that the mass loss rate is now being limited by the energy, what I call the photon tiring. Up until now, we haven't had to worry about the fact that as the photons lift the material off the star, they actually lose energy because they have to do work. But when you do that, when you put that into account in a model, you find that, if you could only go, there's this parameter, which is basically the mass loss rate divided by the luminosity divided by the escape energy per unit mass. So this is just GM over R. And what you find is that you can never get above this because you don't have enough energy from the source base luminosity that you're generating to drive more mass. And if you start to approach that, if you have a nice sort of stellar wind model with the opacity increasing, this is a nice coordinate that goes from 0 at the surface, the radius, to infinity, it's 1. It's just a sort of, it's actually proportional to the gravitational potential. And you can see that for, the wind has a nice wind velocity law for that. But now, if you start to increase this tiring parameter, you find that the wind stagnates. And so the question is, you see, one of the problems is that line-driven winds are very nicely regulated because the line opacity will never let you get to the point where this becomes important. The line opacity always prevents mass loss from ever getting close to this tiring limit. But when you get a continuum driving, there's nothing inherently to stop the radiation driving from being very important, very deep inside the star. So you can immediately imagine that you start to lift material from the star and then it actually stagnates and falls back down on the star. And so in a simple one-dimensional model, this was done with Alain van Merle, who was a postdoc of mine in the late 2000s. we can actually see that material will actually go up and fall back down. This is basically a plot of mass flux, blue for inward, red for outward. And basically you can see material goes up, falls back down, but every once in a while you get some material that makes it a little bit further. And if you follow an individual mass parcel, they actually take trajectories kind of like this, and they eventually crawl their way up. But meanwhile, the luminosity, the energy of the star driving this is varying quite heavily. Of course, this is a very artificial model because it's just one dimension. So what we're trying to do is come up with a way to treat this problem accounting for the multidimensional nature of the structure. When that material falls back down on those shells, it's going to break up. And it's going to look a lot like convection. Matter of fact, you can show that as the star gets close to the Eddington, it becomes convective. But then you get a medium where basically the material is stagnated and it falls back down and it makes this very porous medium. And that porous medium is opaque clumps. And if the clumps are opaque, you can be formally above the Eddington limit, and yet the radiation force is reduced. So it can be below the binding gravity. So this layer can be basically hydrostatic. And at some point, eventually, the clumps become transparent enough that you get an optically thick stellar wind. So that's the basic scenario of this super Eddington regulated, porosity-regulated mass loss. And what's very nice about this recent model is that now we have a formula. If we can just figure out what this porosity length should be, we have a very simple formula that can predict what the mass loss rate should be. Because the effective opacity, the effective radiative force over gravity is just the regular electron scattering divided by 1 plus this scaling formula. At the sonic point, that has to equal 1. That's where the gravity overcomes, the radiation force overcomes gravity. So then you can work out what the tiring parameter is, and it scales like that. You just do some algebra between here and here. And now if you say that what is the scale length of this porosity length? Well, if you say it's something like the gravitational scale height, which is what this is, then you get this formula for this tiring parameter, or this formula for the mass loss rate. And one of the points about this is that what you end up with is that in the denominator, a sound speed instead of the speed of light squared. You get this, and that sound speed is 10 to the 4 times smaller. So this can have a mass loss rate which is much bigger, by a factor of 2 orders of magnitude or 3 orders of magnitude bigger than this standard mass loss rate from line driving. And so the bottom line is, this now becomes a potential way to explain porosity-regulated mass loss. And it's kind of analogous to this picture of Ed Spiegel about photon bubbles, where he uses this analogy of, if you ever see a picture of I couldn't get the movie to run, but if you see a movie of this, this is air being pumped through a bed of sand, and it just pops out in sort of emission where the material escapes. And that's analogous to the way the photons are trying to work their way through this medium. Now, there's lots of papers on this issue of super Eddington stellar winds driven by energy deposition near the star. This is a paper by Elliot Catart. Then when I was in Santa Barbara, I was able to work with him unifying his approach, which basically uses a radiative enthalpy description as opposed to flux driving. This is a really nice paper because it unifies 2 different perspectives about how stellar winds work. And one of the ways you can look at it is that radiative enthalpy, because it's radiative gas behaves like a gamma equal to 4/3 polytrope. A gamma equal to 4/3 polytrope can have a steady state wind. It's like the solar wind at gamma equal to 1 has a nice steady state solution. A gamma equal to 4/3 polytrope has a steady state wind. And so the problem is that you have to properly account for the energy that's being deposited in the envelope. So that's what this paper is all about. All right, so there's our basic picture of how super Eddington winds might work. All right, so steady winds are an idealization. They're subject to instabilities. There's a strong instability, but near the Eddington limit, we can have these giant eruptions. And the key theme that I want to come back to is, I'm sure this all seems very like bizarro world to people here because you don't study stars. But there's a lot of overlapping physics between what's going on in this problem and what you guys worry about. Now, you don't worry about the momentum of photons, but you worry about their energy transport. But you have similar issues about how to actually model the transport of the radiation across media. So that's one area that I think would be really interesting to talk more about. Then the second thing I would say is that I have all this other work that I haven't even talked about today about magnetic fields, magnetospheres, and how how winds get trapped and how analogous that is to the sun. I will say, in final word, right now Steve Kramer and I are working on a project which involves the magnetosphere's transport of particles in a centrifugally supported magnetosphere, very similar to what happens in the Io torus of Jupiter. Material from Io's volcanoes gets ejected, ionized, and becomes part of a torus. And the question is, how does that mass move outward? Because it's rotating so fast that the centrifugal force of co-rotation is faster than the orbital speed, and therefore it wants to be centrifugally driven outward. But the magnetic field is inhibiting that. But if the magnetic field is not ideal, but it has fluctuations on it due to turbulence, then you get a transport. And so Steve has worked a lot on turbulent heating of the solar corona, and that's another example of how the physics of that could also be applicable to transport of ions in these magnetospheres. So the theme comes back to that it's more under the hood that links us, that unifies us than you would expect. And having a person who started out as a solar physicist and went into the dark side of working on stars, literally the dark side. There's a pun there, if you notice. And now we basically see that a lot of the physics has a lot of commonality, and we should at least take advantage of the different perspectives we have from that. Thanks a lot. Can you turn the lights on? Jeff?
Yeah, well, of course there's commonality because it's basically the same physics. The only difference is boundary conditions. Stars and the sun.
Well,
and you're in different regimes. Okay, but my main question is the whole question of magnetic fields and X-ray emission. It's been known for a long time that O stars, which are raised in the winds, which you've been talking about, often are X-ray sources. And the question is whether this is coronal type X-ray emission or whether it's magnetic shocks as opposed to just acoustic shocks in the outer atmospheres of the range of the driven winds. Which do you think it is?
Well, I think as I sort of mentioned in the talk that you can explain the X-ray emission and the broadening. One of the things that you see the big distinction between the width of Capella and the width from Zeta Puppis. And so that tells, it's an instrumental width. So it's all coming from a static corona. Whereas now you see this is coming from an expanding wind with expanding velocities. So that answers the question right there. This cannot be coming from a static corona. This is coming from the expanding region. And it's exactly what we expect from the line-deshadowing instability, giving rise to this very turbulent gas that shocks and then emits X-rays. And the big difference between the sun and hot stars is the mass loss rates are so much larger, the density is very high, and the cooling lengths are tiny. It's a fraction of a stellar radius. So when these shocks occur, they rapidly cool and they give off X-rays, but now all the gas around them is basically bound not bound, it has all these bound atoms, stuff where bound-free absorption becomes impossible. And that's how we explain the X-ray line profiles as basically a radiative transfer problem. But again, one of the big issues that came up is like, how important is the clumping for this bound-free absorption? Well, it turns out if it's clumping from the instability, it's too small scale to make the clumps optically thick and bound-free X-rays. So you can ignore that from that point of view. But I think the empirical evidence as well as the theoretical evidence is that the X-rays that are coming from massive stars, and they also have a different scaling law, as you know. Whereas in the case of the sun, they scale with rotation, but in the case of massive stars, it's velocity. So that tells you, I think, that they're both from shocks of a certain kind, or let's put it this way: I wouldn't say that the sun is not necessarily from shocks; it's from coronal heating. But in the case of the stars, they're shocks. And now you can also have, instead of these turbulent shocks, you can have the case where you have a magnetic loop. The gas gets directed up, and now you have shocks. Whereas before, it's kind of like people in a car traffic where they're bumping up against each other, and they have these small shocks. So the X-rays are half a keV or less. But now when you look at the magnetic massive stars, they have a keV X-rays. And then we look at the colliding winds, they have several keV X-rays. That's because that's more like crossing the median strip of the Autobahn and smashing into people head to head, right? As opposed to having just people bumping into each other.
They also share a synchrotron the MEV electrons.
That's right. That's right. You see in some cases from these colliding wind models, you see tens of keV, and you can't explain that with thermal. So they have to be some sort of non-thermal processes going on as well. But sorting that out is another issue. Colliding winds is a whole other area that I've worked on that is really interesting. I mean, Eta Carinae is a colliding wind, and there's dozens of these colliding students. Tom Maduro did his thesis on, and they're still publishing lots of papers on that. Anyway, yeah. So I'd say the analogies are there, but they're not superficial. When you go from sun to solar type stars, there's a lot of analogies that are almost direct. But when you go from the sun to massive stars, the analogies now you can't make the analogies on a superficial level. You have to look deeper under the physics, under the hood, radiation transport and stuff like that. But that's a good point. Yeah?
Yeah, these massive stars with detected magnetic fields, do they not have calcium K and H and K core emission?
No. Well, no, because they're too hot. They're like 20,000, 30,000, 40,000 Kelvin. So their spectra look completely different. They're O and B type spectral types. But you do see carbon 4, nitrogen 5. Those are all they're all formed in the stellar wind, and they actually could also be influenced by ionization from X-rays from these shocks. But the primary diagnostic of stellar winds, that's one of the other things that's actually very interesting. If you ask, Steve or other people about winds from cool stars, from coronal type winds, they're pretty hard to find. You can see indirect evidence for them. You can see I think it was the Linsky Ayres diagram where they had the transition zone, right? Was that you guys did this diagram about how you could identify places in the HR diagram when you see the X-ray emission? You infer indirectly that they must also have coronal winds, but it's hard to see the direct signature of these winds. The only few cases is when you see this hydrogen wall forming, like in the sorry. But the nice thing about massive stars, I can remember Dave Abbott once gave a talk at one of the solar wind meetings up in Estes Park. And he said, he was asked to give a talk about stellar winds. He says, we know more about the global structure of hot star winds than you guys do about the solar wind, because we can see the whole global structure from the P Cygni profiles. Now, it's a little bit provocative, but in some sense, it's true. It's very hard to get observational diagnostics of coronal winds because they're so low density. And we have this great benefit that we can actually measure them in situ here in the sun, here in the solar case. But from other stars, but you worked on the hydrogen wall, right, Jeff? And and I think you also, Brian Wood, and then I know Gary Zank. I know about primarily from Gary Zank, his work on that as well. But otherwise, it's pretty hard to find direct proof that these other stars have coronal winds. And this is one of the things when Steve does his global theory of heating from all across the HR diagram, right? The mass loss rates, to get the estimates, it's kind of indirect for the coronal winds from other stars because you don't have the observation. Whereas for massive stars, we can be pretty confident. We worry about factors of 2, from clumping, but we know that Zeta Puppis has an order of 10 to the minus 6, a few times 10 to the minus 6. Whether it's 2 times 10 to the minus 6 or 7 times 10 to the minus 6, we argue about till the cows come home. But we know because we can see that in the H alpha, and we can see that not only in the P Cygni profiles, but also in the H alpha emission. Now, one of the things that happens in the massive stars when they have these magnetic fields is that now the H alpha emission that you would normally see just from the stellar wind in the O stars, now that material gets trapped. And so it gets enhanced. And so you see enhanced H alpha emission when they're a magnetic massive star. And you also see enhanced X-rays from the collisions, from the shock collisions. You see harder X-rays and you see more X-ray flux. So it's a really, so that's a whole nother area. And where these fields come from, nobody knows. They're not like the solar cycle. They don't show any activity cycles. They're steady magnetic fields. People think that they may have been formed in the early convective phase, or maybe even interstellar field that's been shrunk down to the size of a star. If you take the interstellar magnetic field and you take it into the size of a star, you get kilogauss. The record is 25 kilogauss for this star called NGC 64. No, that's not Babcock. This is another one. NG 64-2. That star has remarkable, has like almost 30,000 Gauss global dipole field. Pretty amazing. And they may be precursors to magnetars, although there are other people that think that no magnetars are formed during the core collapse. But again, I want to just come back to this idea that, you know, there is a real lot of stuff under the hood that's really similar, and we could learn a lot from each other. So I'm hoping, I'm going to be here till Monday. If anybody has time or chances, you can look at my last name, udel.edu, and that's how you can reach me. Okay? Anybody else have any other questions before? I guess it's already run past.
Maybe just a short one. I was very pleased to see this simple formula for the Burroughs messaging. Is it actually consistent with blue theory, where you have light scattering on the
No, there's no scattering theory. This is a pure geometric theory, right? There's no scattering theory of wave physics in that. It's purely a geometric problem of the clumping. So everything that's done in that, if you saw that, it was just pure optical depth. So you calculate the optical depth. But what's really neat about it, if you look at, you know, all right, I know I kind of went through the math pretty quickly, but it's all really simple. Just calculating optical depth over a stochastic medium. And as far as I know, that's never been done before. So the point is, it's a very general argument. It's not, I applied it specifically to this case, but that should be applicable to interstellar medium or anything that has a lot of density fluctuation. Now, in the case of the sun, most of the stuff that you care about is very subsonic turbulence, and so you don't have that much density fluctuation. Matter of fact, most people who do turbulence theory will use incompressible fluids, right? It's only when you have shocks and stuff like that, compressible turbulence, that you're going to get lots of density fluctuations. But some of the ideas, I think, still might be transportable, or you know, at least give you some insights about how to treat complex media in the sun. For example, variations in opacity due to temperature. Yeah.
So you mentioned interstellar media. Does that mean you could take an idea like this and look at these the measurements of the galactic extinction and reddening and back out the structure?
In principle, this is one of the things I'm trying to get interstellar medium people interested in right now. And I'm only beginning to rattle the cage.
You just solve for that size parameter and you
yeah.
along the pathway.
Exactly. So you see the difference will be that when you have absorption, because of the way geometric optics works for dust, you get reddening, right? Because blue light gets absorbed more than red light. But in principle, if you had a medium which was very opaque, and it was made less opaque because of the porosity of the medium, that would not, there wouldn't be as much reddening in that. That would be more universal, right? Because it's just reducing the, it will be required to look at, because remember, the parameter that's reducing it is the optical depth of that characteristic clumping scale, right? And the porosity length, which is a combination of the scale, the autocorrelation length of the density, and this clumping factor. And so the point is that opacity is different. So different spectral bands will have different levels of porosity, so that it becomes an interesting, complicated problem, but it's one that would be worth playing with and working through. To me, when this came out, I was just like, wow, like a proud papa, right? Because when you get something as simple as that, after doing a relatively complicated calculation, you know that you've sort of grabbed onto something like, you know, allows you some power to sort of do other things. And the question is what is it? You know, we don't know yet. So I'm doing my best to sort of sound the bell and say, let's take a look at this. This could be really interesting way to actually go about extinction in interstellar medium, for example. But the thing is, it only applies to very, very clumpy media that are large density contrast, which happens in these stellar winds because they're so supersonic that they make this tremendously clumped structure. In the sun, you have density fluctuations, but they're not that enormous just from the, there are variations in density from large scales. But you could even in principle apply this same idea, or at least the general idea of porosity. But you have to have a situation where a medium becomes optically thick. And in the case of the solar corona, it's pretty optically thin, which makes it great, But now the question is, I don't think I can't think of any spectral diagnostic where you have to really do radiative transfer in the corona itself, right? Nothing is really optically thick in the corona. But as you get down lower in the atmosphere, of course, there is. And it could be that people who are trying to model radiation transport there could benefit from some of the ideas. At least, we could look at it. So.
Why don't we thank you again?
Okay.
We'll be around.
So I'll be around today, but then also I'm going to come in on Friday morning if anybody's around, and then I'll be available even on Monday in the morning if anybody wants to talk. So just send an email to owocki@udel.edu. Thanks. Thank you for coming, Jeff.